Hey everyone, and welcome to this explainer. Before we jump in, go ahead and take a deep breath. Drop your shoulders a bit and treat this session not as some high-pressure lecture, but just as a calm, guided walk through engineering chemistry. Today, we're looking at the boiler's defenses, specifically how we use internal and external water treatments to protect these truly massive industrial systems. To really understand the scale of what we're dealing with here, I want you to think about something incredibly relatable. Have you ever looked inside an older kettle in your kitchen and noticed that hard, crusty white buildup at the bottom? Well, that is scaling. Now, in a kitchen kettle, it's just a mild annoyance, right? It might make your tea taste a tiny bit off. But an industrial boiler is essentially a massive, highly sensitive, high-pressure kettle. If that exact same buildup happens inside a factory's boiler, it acts as an insulator. It destroys heating efficiency, clogs up the pipes, and honestly, under high pressure, it can actually cause the entire boiler to completely fail.
Okay, let's dive into this. Nature naturally makes water hard. As water travels miles over rocks and through soil, it just naturally picks up dissolved minerals along the way, primarily things like calcium and magnesium. And while that mineral-rich water might be completely fine for a mountain stream, modern, high-pressure industrial boilers absolutely require perfectly pure water. For a boiler, these natural minerals are serious troublemakers.
So what actually happens when that hard water evaporates under all that intense heat? Well, it leaves things behind. We just talked about scales, which are those hard, adhering deposits that stick incredibly tightly to the walls, but the boiler also has to deal with sludges. These are more like soft, loose, slimy precipitates. Then there's caustic embrittlement, which is a condition where the metal actually becomes brittle because of highly concentrated alkaline solutions. And finally, we have boiler corrosion, which is a slow decay caused by dissolved gases, like oxygen and carbon dioxide. It sounds like a lot, I know, but don't worry, engineers have developed some pretty brilliant ways to prevent every single one of these issues.
Think of boiler protection like a VIP club's security system. It operates in concentric circles of defense, and we basically have two main strategies. First is the external treatment. Think of this as the bouncer at the door. It treats the water before it's even allowed to enter the boiler system, removing the vast majority of impurities right off the bat. But, no system is completely perfect. That's where the internal treatment comes in. This is the bodyguard inside the club, mingling in the crowd. It operates directly inside the boiler to handle the tiny, residual trace amounts of hardness that somehow manage to slip past a bouncer.
All right, let's look at Section 1, the outer defense or external treatment. Now, ion exchange sounds like some intense chemistry jargon, but the concept is beautifully simple. Imagine we have a strict dress code. We are simply swapping out the troublemaking particles, the calcium and magnesium ions, for peaceful, completely harmless ones, specifically hydrogen and hydroxyl ions. And we do this by passing the water through specialized, highly porous polymers called resins. Now, what's really interesting about this structure is how the cation exchange resin actually works. See those little acidic sulfonic groups attached to the polymer chain? Well, they are holding on to harmless hydrogen ions. When hard water flows past, this resin is chemically programmed to grab onto positively charged troublemakers, like those calcium and magnesium cations, and then release its harmless hydrogen ions into the water in exchange. So it essentially traps the minerals right there in the polymer matrix.
So the crucial point here is that this bouncer operates in a super smooth two-step process. First, the water passes through the cation exchange bed, where the acidic resins trap the positive mineral ions and release H+. Second, the water moves right along to the anion exchange bed. Here, basic resins trap negative impurities, things like sulfates and chlorides, and they release OH- ions. Finally, the magic happens. The released H+ and OH- naturally combine, and what do they form? H2O, pure, completely demineralized water.
And this brilliantly illustrates the complete setup in action. You've got the two tall columns peacefully doing their work side by side. The hard water flows in, gets stripped of its cations, then stripped of its anions, and pure, soft water flows right out the bottom. And honestly, the best part? When these bouncers get exhausted and their hands are just full of calcium and sulfates, we don't just throw them away. We actually regenerate the cation column by flushing it with a dilute acid and the anion column with a dilute alkali. That resets them and they go right back to work.
Moving right along to Section 2, the inner defense, which is our internal treatment.
Look, even if the external bouncer is 99% effective, that tiny 1% of hardness that slips through, under immense pressure, it will accumulate and cause scaling. So we have to shift our attention to the bodyguard. Internal treatment is all about adding specific, carefully chosen chemicals directly into the boiler feed water. And these chemicals basically have two main strategies for dealing with whatever impurities are left. They can either force the bad stuff to clump together safely into a soft sludge so we can sweep it out, or they can give the impurities a sort of chemical hug, forming highly soluble complexes that just stay dissolved and remain completely harmless.
Let's break this down simply so you have a clear, low-stress mental map for your exams. There are 3 primary conditioning methods you really need to know. First, Calgon conditioning, which uses sodium hexametaphosphate to form soluble complexes. Then, phosphate conditioning, which uses sodium phosphate to create a soft sludge. And finally, colloidal conditioning, which uses organic materials like agar-agar or tannin to surround the precipitates and keep them suspended. Let's look a little closer at each of these, starting with what is arguably the most elegant solution.
Listen, if you want an aha moment for your studies, this is absolutely it. Calgon, which actually stands for calcium gone, is chemically known as sodium hexametaphosphate. It is highly preferred in the industry because it entirely avoids the problem of creating waste. It doesn't actually precipitate the calcium out of the water. Instead, it reacts with the calcium to form a highly soluble complex. It essentially puts the calcium in a chemical straitjacket, keeping it dissolved but totally preventing it from ever sticking to the boiler walls. No sludge basically means no cleanup.
Okay, our second method is phosphate conditioning. Sometimes we actually want to grab those minerals and sweep them out. By adding sodium phosphate, something like trisodium phosphate, to the water, it reacts with that residual calcium and magnesium. But instead of forming a hard, damaging scale, it forms loose, soft, non-adhering calcium and magnesium phosphates. And because this sludge is soft and just naturally sinks to the bottom, the operators can periodically flush it right out of the bottom of the boiler. This simple flushing action is what's known as a blowdown operation.
Finally, we have colloidal conditioning. This one is quite clever, actually, and it uses surprisingly natural organic agents, things like glue, seaweed extract, or tannins. When these are added to the boiler, they act like a slippery shield. They literally coat the outside of the scale-forming particles, keeping them in a suspended colloidal state. And because they are coated and super slippery, they simply cannot stick to the hot boiler walls to form scale. So just like the phosphate sludge, they are easily swept out during routine blowdown operations.
So, to recap our journey today, we've got our external bouncers, the ion exchange resins, removing the bulk of the threat. And we've got our internal bodyguards, Calgon, phosphates, and colloids, managing whatever manages to slip through. It's a really perfect system of layered defense. And honestly, it's a pretty great metaphor for learning, too. Having layers of protection, like reading the text, watching an explainer like this, and taking calm, focused notes, it creates a resilient system in your own mind that can handle the pressure of literally any exam.
As we wrap up this explainer, I want to leave you with this thought. Knowing how beautifully these external and internal defenses work together to protect something as massive and complex as an industrial boiler, where else in your life could you use a layered defense strategy to protect your own energy and focus? Thank you so much for taking this calm walk through water chemistry with me today. You've got a really solid grasp on this material now. Keep up the great work, and as always, stay curious.